In this video, we are going to show you how the drinking bird toy applies the first law of thermodynamics. But before that, let us look at what is the first law of thermodynamics. This guy here came up with a full statement of the first law of thermodynamics, which states that energy can neither be created nor destroyed, but it can only be transformed from one form to another. Sounds deep, huh? Our drinking bird here is amazingly a heat engine. A heat engine is a system that performs the conversion of heat or thermal energy to mechanical energy, which can then be used to do mechanical work. An example of the heat engine in daily life would be the steam engine, which you'll find in steam trains. Here, we have built our own drinking bird model using methanol, two 10 ml volumetric flasks, a glass tube, rubber tubing, and a bendable wire. Before starting our experiment, we set up our heat engine or drinking bird so that it's tilted at an angle, as shown here. But why? We'll explain it to you later after you have gained more understanding on the drinking bird mechanism. The drinking bird that we have built here is some sort different from the ones that you can find from stores. Both of them work based on temperature difference between the top and bottom bulbs. The difference is that temperature difference is created through evaporative cooling of the top bulb in this drinking bird, while in our case, we will be heating the bottom bulb of our drinking bird model. Since this is a closed system, the energy balance delta U equals to Q plus W applies. Our analysis can thus be divided into 4 parts. Part 1. We heat the bottom bulb using a Bunsen burner. The system receives heat, thus Q is positive. Upon heating, the methanol molecules in liquid phase increase in kinetic energy to a point that some of the liquid molecules gain enough heat of vaporization to overcome liquid surface resistance to become vapor. More and more vapor is formed here, and since the vapor also receives heat, it expands and pushes the column of methanol in the tube up towards the top bulb. Thus, expansion work is done by the vapor onto the liquid surface. Notice that our model tilts as methanol liquid passes the pivot point. Rotational work is involved here to overcome rotational inertia of the structure. This rotational work is mainly due to the mass transference of methanol liquid toward the upper bulb across the pivot, i.e. the shift of center of gravity. Part 3. A combination of expansion work by the vapor and rotational work due to mass transference of methanol liquid causes the drinking bird to eventually tilt to a nearly horizontal position. At this point, voids or spaces exist between the bottom bulb, the glass tube, and the upper bulb. This allows for pressure equalization between the two bulbs. There is no net force preventing the methanol liquid from falling back to the bottom bulb. Part 4. Methanol liquid falls back to the bottom bulb due to action of gravity. The drinking bird model tilts back to its original position. This is again due to rotational work done by the methanol liquid traversing past the pivot point, resulting in a change in the center of gravity of the model. At the beginning of the video, we mentioned that the drinking bird has to be tilted at an angle for it to perform work. But why? Work involved here is rotational work, which means torque plays a part in the rotational motion of the bird. If we start at the upright position, there would be no torque, and our drinking bird won't work.